A commonly used method to evaluate the accuracy of a classification model is a graphical representation called Receiving Operator Characteristics Curve, for short ROC curve. The ROC curve shows the quality and robustness of the classification model as defined by the false positive rate and true positive rate, or in other words, sensitivity and 1 minus specificity. Many scoring metrics measure the performance of a classification model for only one specific value of the threshold applied to the probability of the positive class. However, this is just one possible working point for the classification model. The ROC curve attempts to provide a more comprehensive view of the model performances for different classification thresholds. Here you see the ROC curve. On the x-axis, you see the false positive rate, and on the y-axis, the true positive rate. This blue line is the ROC curve of the model we have trained. This black line is the ROC curve of a random classifier. So how are all these different values of the false positive rate and the true positive rate calculated? Let's have a look. For each input event, a classification model produces a class probability that determines the class assignment. By default, the events are assigned to the positive class if the probability of the positive class is 0.5 or higher, and to the negative class otherwise. If we increase this classification threshold, fewer data points will be assigned to the positive class. If we decrease the threshold, more events will be assigned to the positive class. Here we see a number of events ordered by their probabilities to belong to the positive class. By default, the value of the classification threshold is set to 0.5, and here are the corresponding assignments to the two classes. Next, we decrease the threshold value, for example, to 0.2. Now we see that the class assignment changes for these data points with a probability for the positive class falling between 0.2 and 0.5. Finally, let's increase the classification threshold to 0.7. Now, only those events will be assigned to the positive class because their probability for the positive class is greater than 0.7. As you can see here, the true positive rate and the false positive rate also change every time we change the value of the threshold. The true positive rate is calculated as the number of correct predictions to the positive class divided by the total number of events in the positive class. The false positive rate is calculated as the number of incorrect predictions to the positive class divided by the total number of events in the negative class. For these threshold values, let's plot the false positive rates on the x-axis and the true positive rates on the y-axis. This dot represents the performance of the model for the default threshold, this dot stands for the threshold of 0.2, and this dot for the threshold of 0.7. If we now connect these dots, we have a sketch of the ROC curve. In reality, the ROC curve is drawn based on many more threshold values and therefore many more pairs of these two rates. The ROC curve of a perfect classifier would move along the axis to reach this point for the perfect threshold lying in this corner. Here, the true positive rate is 1 and the false positive rate is 0. The closer the curve of our model is to that point, the better the model is performing. In the case of a random classifier for a two-class problem, all events have the same probability for the positive class independently of their actual class values. By varying the value of the classification threshold, the ROC curve becomes this straight line. This is the worst performance your model can produce. If the ROC curve of your model lies below the line of the random classifier, then you probably made a mistake in building the ROC curve. The ROC curve has a few advantages as a model evaluation technique. Firstly, it allows you to visually compare different models in terms of performance. If we have more than one model, the model with the highest ROC curve will be the best performing one. Secondly, if the eye comparison among model curves becomes complicated, we can always use the area under the curve, for short AUC measure. The AUC measures this area here. It is 1 for the perfect classifier and 0.5 for the random classifier. Thirdly, the ROC curve allows us to choose the threshold that produces the best performance. One method to select the optimal threshold is to minimize the Euclidean distance between the curve and the point in the top left corner, indicating perfect model performance. The point in the curve that minimizes the distance is this tangent point shown here. In this video, we have shown how an ROC curve is drawn, given the actual class values, probabilities of the positive class, false positive rate, true positive rate, and classification thresholds. We have also shown the robustness of the ROC curve as a method to quantify and compare model performances.